silicon. Now, I'm going to explain the Czochralski's crystal growth method. The Czochralski's crystal growth process is a widely used method for growing single crystals, particularly silicon, which is essential in semiconductor manufacturing. Here is a breakdown of the process. It starts with a small crystal seed, as you can see over here, indicated over here, which initiates the crystal growth. The seed crystal is dipped into a molten material contained in a crucible. Like for example, if we talk about silicon, then the melting point of silicon is approximately 1400 degrees C, slightly above 1400 degrees C. So silicon is melted above that temperature, and this crystal seed is dipped into the molten material, which is contained in a crucible, indicated over here. The material, we heat the material, for example, silicon, beyond its melting point using heaters surrounding the crucible. The seed crystal is carefully lowered into the molten silicon over here. Once the seed touches the melt, it begins to cool slightly, initiating the growth of the single crystal silicon. And then the seed is then slowly pulled upwards at a particular rate and rotated simultaneously. This pulling process is done under controlled conditions to ensure that the crystal grows in a uniform manner without any kind of defects. And this process is actually demonstrated over here as well. So the continuous pulling and cooling cause the material to solidify. So we pull it and we rotate it, and then the melt has a particular temperature. So when we start pulling the seed, it starts the material to cool and causes the material to solidify, forming a long cylindrical ingot of single crystal material, which is also seen on the right side. We call it the silicon ingot. This method is ideal because the pulling process ensures that the atoms arrange themselves in a perfect crystalline structure as the material cools. Now here are the key features of the Czochralski's growth method. First, it's a control method. By controlling the temperature, the pulling rate, and rotation speed, the size and quality of the crystal can be managed. And secondly, this Czochralski's process is known for creating single crystal, or we can call it monocrystalline silicon material, with minimal imperfections, which is essential for electronics manufacturing. The process is famously used for growing silicon ingots, which are later sliced into wafers to manufacture semiconductors used in electronics like computers and smartphones. Here is another depiction of the same process. The Czochralski's process is critical for producing large high purity single crystals, especially for materials like silicon used in the semiconductor industry. The feed material, for example silicon, is placed in a cylindrical crucible. You can see it over here. It's in granular form, so it's placed inside this crucible over here, and then it's heated to above the melting point of silicon using either resistance heaters or radio frequency heaters surrounding the crucible. Once this raw material or the polysilicon is fully molten, a small seed crystal, typically a few millimeters in diameter, is lowered into the surface of the molten silicon. The seed crystal serves as the foundation for the growth of larger single crystal silicon ingot. So the seed crystal is dipped into the melt, and then the seed crystal is gradually pulled upwards while the melt solidifies onto the crystal in a controlled manner. As the silicon continues to grow, its cylindrical shape is maintained by adjusting the pulling speed and the temperature. And the result is a long cylindrical single crystal silicon ingot. As we already discussed, that the rate of pulling and the temperature of the melt are precisely controlled to ensure that the crystal grows in a uniform defect-free manner, and the heaters maintain the material at the right temperature for continuous crystal formation. And here is this a different representation of the same process. We can see it over here as well, starting with the polysilicon chunks, and then here is the silicon single, the crystal seed dipped into the molten state, and then we start pulling it, rotating it. The pulling rate, the rotation rate, and the temperature of the melt defines the diameter of this silicon ingot. Here is another depiction of the same process. So high purity silicon is melted in a crucible made up of silicon dioxide. So as you can see, this is the quartz crucible, silicon dioxide crucible within a furnace, and a small pre-existing single crystal silicon attached to a seed holder is dipped into the molten silicon. The crucible is made up of silicon dioxide. It can hold the molten silicon, and it's heated externally using heaters surrounding the crucible. The entire process is conducted in an inert atmosphere, usually by the introduction of inert gas like argon, to prevent contamination. And silicon monoxide and carbon monoxide byproducts may be generated, and they can be removed as well from the chamber. A thermal shield is actually also applied, which helps maintaining a stable temperature gradient, which is crucial for high quality crystal growth using the Czochralski's growth method. And here is another depiction of the same process. As you can see there, the pull rate, the melt temperature, and the rotation rate are critical over here. This image highlights the key aspects of impurities in Czochralski's silicon crystal growth method. Oxygen is the most prevalent impurity in the Czochralski's growth method, typically with concentrations in the range of 5 to 10 to the power of 17 per centimeter cube. Similarly, carbon concentrations are much lower, in the range of 5 to 10 into 10 to the power of 15 per centimeter cube. The solubility of oxygen in silicon is high, approximately 10 to the power of 18 per centimeter cube at the melting point. As we know that we have to melt the silicon above 1400 degrees C, and the solubility of oxygen is high at that temperature, but it decreases drastically at room temperature, creating a tendency for oxygen precipitation. High oxygen concentration can result in the formation of electrically active defects, which may affect the semiconductor properties. And this diagram shows the temperature gradient in the crystal growth furnace with side and bottom heaters. So you can see the side heaters and the bottom heaters over here. These side and bottom heaters regulate the melt and crystal growth environment. So these factors impact the quality of single crystals used in semiconductor devices. This slide provides insight into the role of oxygen in Czochralski's silicon growth process, and it also shows its benefits. Oxygen in the Czochralski's growth method acts as a gathering agent, trapping trace metal impurities within the crystal, a process which is also known as internal gathering. And this enhances the crystal purity. Also, oxygen helps in pinning dislocations. These are like slightly advanced concepts in material sciences. And these pinning of the dislocations make the crystal structure stronger and more resistant to defects. Oxygen precipitates within the wafer core, reducing stacking faults, making the silicon more robust, especially during thermal processing. Also, the presence of oxygen makes the Czochralski's grown silicon highly resistant to thermal stress, which is critical in the manufacturing of integrated circuits. So, due to the enhanced mechanical and thermal properties imparted by oxygen, Czochralski's grown silicon is preferred for integrated circuit production, especially in processes involving high temperature steps. Like, for example, if you want to grow MOSFETs, you might like to perform oxidation and then ion implantation steps, and the ion implantation might then require annealing at high temperatures above 1000 degrees C. So if the wafers are mechanically and thermally stable, you can perform these kind of processes. So these points actually highlight the importance of oxygen in improving the mechanical properties and the thermal stability of Czochralski's grown silicon, making it ideal for semiconductor applications. So actually the oxygen impurities in the Czochralski's grown silicon can go both ways. It can be useful and it could be counterproductive as well, depending on the application. Here is an actual picture of the Czochralski equipment to get an idea about the dimensions. The equipment dimensions for industrial silicon productions typically include a chamber height, which could be like 2 to 3 meters, then a chamber diameter which could be 1 to 1.5 meters, a crucible which can have a diameter from 18 to 24 inches for 300 millimeter wafers, and a height of like 12 to 20 inches. The crystal length could be 1 to 2 meters, and the crystal diameter sizes are like 100 millimeters, 200 millimeters, 300 millimeters, up to you can say 450 millimeters. And this slide gives you an idea about the height of the silicon ingot. So this person apparently seems like a tall person, and you can see that this silicon ingot has a height which is like, this person might be around 6 feet, so this silicon ingot appears to be taller than that, around 6.5 feet I would say. So the entire system, including heaters, the rotational mechanism and cooling systems for the Czochralski's growth equipment might actually occupy several square meters, like an entire lab. This slide discusses how impurities or dopants are added to a molten semiconductor during the fabrication process, such as for doping the material to make it either P-type or n-type. So far we discussed the growth of silicon crystal ingot using the Czochralski growth method, but also you know that when we buy wafers, it could be intrinsic, it could be p-type, or it could be n-type. So how do you make it p-type or n-type? We add impurities in the semiconductors, and these impurities dope it either n-type or p-type, depending if they are pentavalent or trivalent impurities. So let's start with the basics. What are impurities? Impurities are atoms or elements added to a semiconductor material to change its electrical properties, usually to make it a better conductor, and this process is called doping. Now the question is, how do impurities behave in a melt as compared to when they are solidified? Like for example, we melt the silicon in a crucible and above like 1400 degrees C, then how are the dopants going to react, or you can say act, in the molten state inside the crucible as compared to when we solidify the molten silicon into single crystalline silicon ingot? So when impurities are added to the molten semiconductor, they don't always want to become part of the solid material. Impurities have a tendency, like mostly, to stay inside the liquid, the liquid or the molten silicon materials. Many impurities prefer to stay in the liquid rather than becoming incorporated into the solid structure of the semiconductor, and this tendency is described by segregation, or you can say segregation coefficient. What is segregation coefficient? Segregation coefficient demonstrates the behavior of impurity, or how much of it gets incorporated into the solid versus how much stays in the liquid, and this measurement is called segregation coefficient, or you can say segregation coefficient is the ratio of impurity in the solid to impurity in the liquid. Like we talked about this process, let's go to some slide, like for example this one. So if we add impurities into this melt, segregation coefficient is the ratio of impurities in this solid, the silicon ingot, to the impurities in this liquid. So a low, and we represent the segregation coefficient with K. So a low value of K, which is close to 0, means that most of the impurity stays in the liquid, and a high value of K close to 1 actually implies that the impurity distributes equally between the solid and the liquid. And some examples of impurities are aluminum, boron, and phosphorus in silicon. For aluminum, the segregation coefficient is 0.002, meaning that it almost always stays in the liquid with very little getting incorporated into the solid. Now as compared to that, the segregation coefficient of boron is 0.8, meaning that it shows less preference for staying in the liquid, and it's more likely to be found in the solid. So it's comparative. So it means that boron has a better tendency getting into the solid, into the single crystalline silicon ingot, as compared to aluminum. And then the segregation coefficient of phosphorus is 0.35, meaning that it has a moderate tendency to go into the solid. However, there is another problem with phosphorus. Phosphorus also evaporates from the melt at a high rate, which adds complexity to its behavior during the process. So, I mean, the takeaway point is that we know that in order, for example, compare boron versus phosphorus doping of silicon. We know in order to dope silicon p-type, we need to add a trivalent impurity such as boron. And in order to dope silicon n-type, we need to add a pentavalent impurity such as phosphorus. So looking at the segregation coefficients, it means that it's going to be easier to dope silicon p-type with boron as compared to dope it n-type with phosphorus. So in other words, you can say that the takeaway point of this slide is that impurities have different preferences for being in the solid semiconductor versus the liquid melt, and this behavior is characterized by the segregation coefficient. It's crucial in controlling how much of the impurity ends up in the final solid material. Some impurities like aluminum prefer to stay in the liquid, while other impurities like boron have a higher chance of being incorporated into the solid. Here I'm going to demonstrate the how to define the dopant concentration nomenclature. So like how to classify materials into lightly doped, and heavily doped materials. We know that for n-type doping, we use a pentavalent impurity like phosphorus, and similarly for p-type doping, we use a trivalent impurity like boron. If the doping concentration is less than 10 to the power of 14 per centimeter cube, we classify it as very lightly doped materials, and we represent it with n minus minus, where minus minus is used as the superscript. Similarly, we can have like very lightly doped p-type material represented with p minus minus. Similarly, doping concentrations in the range of 10 to the power of 14 to 10 to the power of 16 can be classified as lightly doped material, and we represented with n minus or p minus. Doping concentrations in the range of 10 to the power of 16 to 10 to the power of 19 is classified as doped, and we represented with n or p. Similarly, doping concentrations with greater than 10 to the power of 19 per centimeter cube are classified as heavily doped, and we represented with n plus or p plus.